Okay, so hi everybody. Today I want to talk a little bit more about the properties of electromagnetic waves. Last time we talked mostly about the wavelength of electromagnetic waves and their oscillation frequencies, which are important parameters that define the electromagnetic spectrum. Today I want to talk about a couple other parameters that are important for electromagnetic waves, namely their intensity and their polarization. Both of these properties are tied to the strength of the electric and magnetic fields in the waves. When we talk about frequency and wavelength, we're talking about how the fields change with position and with time. But one thing we haven't talked about much is just how strong these fields are. How strong are these oscillations in the magnetic field? Just how strong are the oscillations in the electric field? That's what we're going to focus on today. Now, turns out that there are some things that are basically forced to be the case about these electric and magnetic fields. Just like we couldn't set the frequency and the wavelength independently, because both of these things are connected through the speed of light, it turns out the electric field and the magnetic field are also two things that cannot be set independently. The nature of this propagating disturbance and the fact that electric fields, when they change, make magnetic fields, and when magnetic fields change, they make electric fields, means that there's a direct relationship between the magnitude of the magnetic field variations and the magnitude of the electric field variations, which basically mean there's a relationship between the amplitude of the oscillations of the electric field and the amplitude of the oscillations in the magnetic field. And that relationship again involves the speed of light. It is basically this relationship down here. The amplitude of the electric field oscillation, which we designate here with E naught, is the speed of light times the amplitude of the oscillations in the magnetic field, B naught. So again, these are amplitudes. These are the maximum magnitude of the electric field and the maximum magnitude of the magnetic field. These things oscillate back and forth, so sometimes they're positive, sometimes they're negative, but their amplitudes have this relationship whenever the wave propagates in vacuum. It also works pretty well when the wave propagates in air and most other materials. We'll see cases where this isn't quite the case. But it means once we've specified the electric field, we know what the magnetic field strength has to be. They're not independent numbers. And that's just due to the way the electric and magnetic fields interact. And also, what's cool is this also works from a unit perspective. Remember, the units of an electric field are newtons per coulomb, or kilogram meter per coulomb second squared. Rearrange that, pull out a meter per second, which is speed, you get meter per second, kilogram per coulomb second. That's a Tesla. So this works. And it means that if you know the strength of the magnetic field, you also know the strength of the electric field. And that's relevant in various cases that we'll get into. But on top of this, there's not just a relationship between the magnitudes of the electric and magnetic fields, that is their strength, there's also a very prescribed relationship between what direction they point. Turns out, as in these pictures that I've been showing you, the electric field is pointing up and down, while the magnetic field points in and out. And this wave is propagating from some source to some other object. That is not just something I did to draw this. That's actually enforced by the equations that govern electric and magnetic fields. If you have a thing like this, the direction of the electric field and the direction of the magnetic field have to be 90 degrees from each other. And the direction of the electric field and the direction of the magnetic field have to be 90 degrees from the direction the wave is moving in. So basically, if we have the wave propagating in the x-axis, the electric field and the electric field points in the y-axis, the only direction the magnetic field can point is in the z-axis. And this is, again, just a fundamental property of how these waves interact, or how the electric and magnetic fields work together to produce this wave. You cannot have any component of this oscillating electric field, if it's part of the wave, pointed anywhere but 90 degrees from the direction the wave itself is propagating. The magnetic field can't do that either. And both the electric and magnetic fields have to be 90 degree, make an angle of 90 degrees away from each other. I could not draw an electromagnetic field, or sorry, I can draw an electromagnetic field where these rules aren't obeyed, but it won't be a proper electromagnetic wave. That is, if I drew a wave where the electric field is going up and down like this, I cannot draw the magnetic field going down and up. It needs to go in and out of the board. If I want, I could potentially make it go left and right, but in that case, the wave would be coming out of the screen instead of moving across it. So it means once we know the direction of the electric field, we also have a sense of what the direction of the magnetic field is. And we have some constraints on how the waves propagate. Now, the wave could be propagating to the left or to the right, but you can at least figure that out. You at least have some constraints on this. And this property, that basically the directions of everything are kind of interrelated, connects with something else, which we'll talk briefly about now, but talk a little bit more about later probably, which is this concept of polarization. Electromagnetic waves have a property called polarization in addition to intensity and frequency. Polarization is just a sense of what direction the electric field points. So if we have a wave traveling from left to right, one way that can work is you have an electric field that points alternating up and down. This is what can be called a vertically polarized wave because the electric field points vertically. The other possibility is we could have the electric field point in and out. In this case, the magnetic field points up and down. But the electric field, since it points in and out, we can describe that as a horizontally polarized wave. And just to say, these aren't the only options. You could have it tilted, be partially pointing up and partially pointing out. That's allowed. Those are given different names, but it's easy to talk about a vertically and a horizontally polarized wave. And this is important because it can affect how this wave interacts with materials. Remember, so imagine we have a positive charge just sitting down here. As this electromagnetic wave comes by, the electric field will pull on that charge and cause it to move up and down. And you might say, oh, if it's moving up and down, the magnetic field also plays a role. It does, but remember, it does, but it turns out it's kind of a weaker role. Primarily, the charge gets dragged back and forth, mostly by the electric field in most cases. Magnetic field can be important in other situations. So in this case, the charge gets moved up and down, just like the direction of the electric field. In this case, where the field goes in and out, what do you think happens here? Well, the charge moves in and out. So these different types of waves, they both cause charges to move, but they cause them to move in different directions. And this has implications for how these charges will interact, how these waves will interact with matter. Just to give you a quick example of that, let's consider radio waves where, again, this picture of charges just moving works pretty well because we can ignore quantum mechanics. Imagine we had a series of vertical wires, just vertical wires, normal metal, and we're going to shine a radio wave on them. It's something with a low frequency, but it's perfectly happy to drive currents in wires. We're going to consider a radio wave that's hitting this collection of vertical wires. Everything, we're going to say it's got the same frequency, it's got the same amplitude, but it has different polarization states. One wave has vertical polarization, one wave has horizontal polarization. Which one's going to interact more with these wires? I would ask you to think about that. Would the wave with vertical polarization interact more? The wave with horizontal polarization interact more? Oh, does it really not matter? The answer is, in fact, the wave with the vertical polarization interacts more with this set of wires. The reason being, if it's vertically polarized, the electric field goes up and down. It grabs charges in these wires and happily pulls them up and down the wires, creating lots of current. That current can then drive changes in the electric and magnetic fields, which then affect how the wave propagates. So a vertical polarized wave hits these and interacts with it strongly. In fact, this works more or less like a solid sheet of metal. This is reflective to vertically polarized waves. If we take a horizontally polarized wave, it will grab the charges and try to move them back and forth. But it can't, because there's no place for them to go. They'll move a little bit. There'll be a little bit of current, but it's just not as efficient. So this thing doesn't interact very well with horizontally polarized radio waves. It just acts more or less like nothing. So if you shine both, so this means this thing acts like a mirror for vertically polarized light, but acts like basically nothing for horizontally polarized light. And that means that polarization can be isolated, can be filtered by setting up situations like this. And this not only happens in radio waves, it happens in light. When you have light bouncing off other objects, it can affect its polarization state. And again, this is something we'll talk a little bit about in the rest of this section. Moving on, but for now, what I want to focus on here is a more basic property, which is the intensity of this radiation. And intensity is one of those words that physicists use that means a specific thing, but it also has kind of a more colloquial sense. Like, lots of us know when light is intense or not. And this is actually the kind of sense that we're going to talk about. Fundamentally, all intensity is a measure of an electromagnetic wave's ability to carry energy, or how much energy it actually carries. The thing is, these electromagnetic waves do carry energy. And it's fairly easy to see that that must be the case. If I take a positive charge here and shake it back and forth, it produces an electromagnetic wave, an oscillation in the electric and magnetic fields that'll cause another charge some distance away to shake back and forth, or up and down in this case. This charge, before I started shaking the source, this charge wasn't moving. It had no kinetic energy. If I start shaking this thing starts moving. It starts having some amount of kinetic energy. That energy had to come from the source, and the way it was transported was through the electromagnetic wave. That wave must therefore transmit energy. It must carry energy from the source to the receiver. And the intensity is just a measure of how much energy this thing transports. It fundamentally has units of energy per unit time per unit area. So its fundamental units are watts, energy per unit time, divided by meters squared. The reason it has to work like this, because this is a transport process. It's not that this thing has energy, it's a disturbance in the electric and magnetic fields that's propagating. So it does have energy, but what's more relevant is how it carries that energy from one place to another. So the motion of energy is not in joules, it's in joules per second. That's how quickly energy is being transported. And how much of this energy you collect depends on how much light you correct. That depends on area. So the standard units for this are watts per meter squared. We'll see a few examples just to try and make that a little clearer. Now, it turns out that intensity parameter is directly related to the magnitude of the electric and magnetic fields. This is because these are the things that are going to move this charge. These are the things that carry that energy. And there's a variety of expressions for this, but fundamentally the average intensity of an electromagnetic wave is the product of the electric field magnitude, the magnetic field magnitude, divided by 2, and divided by that fun mu naught parameter. Now, this is one way to write it. You can use this rule, E naught equals CB naught, to rewrite this as just a function of the electric field magnitude or the magnetic field magnitude, whichever one you're given. And we'll see a couple of problems that show you how to use this formula. But it means if you know how much energy is being transported, you can figure out what the electric field strength is. If you know what the electric field strength is, you know how much energy is transported. So the magnitudes of these fields tell us something about how well or how much energy it transports, which is rather useful. Now, so this quantity is going to show up a lot, and so it's worth having a sense of this. One thing to be clear about this is that in typical cases, the intensity of electromagnetic waves falls off with distance from the source. And there's good reasons for that. If you have a source of electromagnetic radiation, be it light, be it a light bulb, be it a star, be it anything, that thing is producing light. It is releasing a certain amount of energy every second in the form of light. That can be written in terms of a power, which we'll call P. That light then goes off in all directions. Some of it heads up, some of it heads down, some of it heads to the left, some of it heads to the right. Now, as that light goes out, it spreads out. That energy gets dispersed. Now, if you're a distance d from the source, the area the light is spread out over is basically a sphere of radius d, which means that a distance d from the source, you're over a surface area of 4 pi d squared. So the intensity of light is just the power, that is the amount of energy released every second from the source, divided by 4 pi times the distance squared. So as the distance gets bigger, the intensity goes down, and it goes down quickly. If you double the distance, the intensity goes down by a factor of 4. Now, this is just geometry. This is nothing specifically about how electromagnetic waves work. It's just energy conservation. And the rules of electromagnetism obey this because everything has to obey energy conservation. Okay, so that's just introducing you to the remaining important concepts about electromagnetic waves, their polarization and their intensity, and also some of the relationships between electric fields and magnetic fields. In addition, uh, now you can go and there will be a couple of worked problem examples where we explore some of these relationships. Thank you for your time.